NENOMATICA, where mathematics meets YouTube excellence. Welcome! In this lesson, we will understand the floor function, and then solve a problem step by step. We will build an intuition first. The floor of x, written as floor of x, is the greatest integer less than or equal to x. It maps real numbers to integers. Here is the core rule that unlocks almost every exercise. Floor of x equals n if and only if n is less than or equal to x, and x is less than n plus 1. Let's visualize that on a number line. If the floor of x equals 2, then x must lie from 2 inclusive up to 3, but not including 3. The floor function is a step function. It stays constant between consecutive integers and jumps at each whole number. Now, let's solve our example together. We want to solve floor of 2x minus 1 equals 3. We will turn the floor equation into a compound inequality using our rule. By the rule, floor of something equals 3 means that expression is at least 3 and strictly less than 4. So 3 is less than or equal to 2x minus 1, and 2x minus 1 is less than 4. Next, add 1 to all three parts. That gives 4 is less than or equal to 2x, which is less than 5. Finally, divide all parts by 2. We get 2 is less than or equal to x, and x is less than 2.5. So the solution set is the half-open interval from 2 to 2.5. In this lesson, we will build an intuitive picture of the floor function. The floor of x, written as floor left x right, returns the greatest integer less than or equal to x. We will analyze it interval by interval and draw its graph as a staircase with closed circles on the left and open circles on the right. Step 1. Focus on the interval from -2 to -1. For every x here, the greatest integer less than or equal to x is -2. So f of x equals -2 on this entire interval. We write -2 less or equal x less than -1 implies floor of x equals -2. Step 2. Now, the interval from -1 to 0. Here the greatest integer less than or equal to x is -1. So f of x equals -1 on this whole interval. We write -1 less or equal x less than 0 implies floor of x equals -1. Step 3. Consider x from 0 up to, but not including 1. The floor value is 0 all along this interval. So 0 less or equal x less than 1 implies floor of x equals 0. As a quick check, floor of 0.99 equals 0, and floor of 0 equals 0. Step 4. Move to x between 1 and 2. The floor is 1 on the entire interval. 1 less or equal x less than 2 implies floor of x equals 1. Step 5. Now x from 2 to 3. Here the floor is 2 throughout the interval. 2 less or equal x less than 3 implies floor of x equals 2. We can summarize the entire staircase with a single rule. For any integer n, if n is less than or equal to x and x is less than n plus 1, then floor of x equals n. When we combine all these intervals, the graph looks like a staircase with closed circles on the left ends and open circles on the right ends. In this lesson, we will learn the ceiling function, the core inequality algorithm to solve problems with it, see its step function shape, and avoid a common notation pitfall. Step 1. Definition. The ceiling function maps real numbers to integers. We write f of x equals the ceiling of x. The ceiling of x is the smallest integer greater than or equal to x. Step 2. The fundamental inequality. If the ceiling of x equals n, if and only if x is strictly greater than n minus 1 and less than or equal to n. This is the core algorithm we will always use to solve equations with the ceiling function. Now, let's see it as a picture on a number line for a specific n, say n equals 4. We will highlight the open endpoint at n minus 1 and the closed endpoint at n. This shows that all x in the open to closed interval produce the same ceiling value n. Step 3. Understanding the step function. The function f of x equals the ceiling of x is constant on each open to closed interval from n minus 1 to n. It jumps by 1 at every integer. Let's draw a small portion of the graph. Step 4. Important notation note. In many contexts, the square bracket of x can mean the floor function. We will avoid that confusion by writing ceiling explicitly with the left and right angles around x. That is, ceiling of x is written with the angled brackets. Summary. To solve ceiling of x equals n, use the inequality n minus 1 less than x less than or equal to n. For example, if the ceiling of x equals 5, then 4 is less than x and x is less than or equal to 5. Let's display the rule and then solve the example on a number line. We highlight the open point at 4 and the closed point at 5. The solution set is all real x strictly bigger than 4 and up to and including 5. Bonus check. If the ceiling of x equals -2, then x is greater than -3 and less than or equal to -2. Recap. The ceiling function maps real numbers to integers and is constant on open to closed intervals ending at each integer. The algorithm is simple. If the ceiling of x equals n, then x lies between n minus 1 and n, open on the left and closed on the right. Practice with a few more values of n to build strong intuition. Example. In this lesson, we will graph the ceiling function step by step using clear interval reasoning. Our problem is to graph f of x equals the ceiling of x, focusing on the intervals from -3 to 2. We'll build the graph one horizontal step at a time. Let's set up an xy coordinate plane and reserve space for our step graph. We'll label integers on the x-axis from -3 to 2 and y values from -2 to 2. Here's the key idea we'll use repeatedly. The ceiling of x is the smallest integer greater than or equal to x. Step 1. On the interval -3 is less than x, and x is less than or equal to -2, the ceiling is -2. Let's place a horizontal segment at y equals -2 from x equals -3 to x equals -2 using an open circle at the left and a closed circle at the right. Open for strictly less than at -3 and closed for less than or equal at -2. Step 2. For -2 is less than x and x is less than or equal to -1. The ceiling equals -1. We draw the horizontal step at y equals -1 from x equals -2 to x equals -1, open on the left, closed on the right. Step 3. For -1 is less than x and x is less than or equal to 0. The ceiling equals 0. Let's add the segment at y equals 0 from x equals -1 to x equals 0. Again, open on the left, closed on the right. Step 4. For 0 is less than x and x is less than or equal to 1. The ceiling equals 1. We add a horizontal step at y equals 1 from x equals 0 to x equals 1, open then closed. Step 5. For 1 is less than x and x is less than or equal to 2, the ceiling equals 2. We'll draw the final step at y equals 2 from x equals 1 to x equals 2 with the correct open and closed endpoints. In this lesson, we will graph and understand the function f of x equals floor of x plus ceiling of x. We'll define floor and ceiling and then analyze the function on intervals, discover the general rule, and finally build the full graph step by step. Let's analyze on the interval from 0 to 2. At x equals 0, both floor and ceiling equal 0, so f of 0 is 0. For numbers strictly between 0 and 1, floor of x is 0 and ceiling of x is 1, so f of x equals 1. At x equals 1, both floor and ceiling equal 1, so f of 1 is 2. For numbers strictly between 1 and 2, floor of x is 1 and ceiling of x is 2, so f of x equals 3. Now, let's generalize. When x is an integer, say x equals n floor and ceiling both equal n, so f of n equals 2n. When x is not an integer, and lies strictly between n and n plus 1, floor of x equals n, ceiling of x equals n plus 1, so f of x equals 2n plus 1. Putting it all together, we can write a clean, piecewise form. If x is an integer, f of x equals 2x. If x is not an integer, f of x equals 2 times the floor of x plus 1. Let's draw the graph over a few integers. We'll use the x range from -3 to +3. For each open interval from n to n plus 1, we draw a horizontal segment at height to n plus 1 with open circles at both ends. At every integer x equals n, we place a filled dot at 2n. Now, let's zoom our attention back to the interval from 0 to 2 to match our earlier analysis. Between 0 and 1, The graph sits at y equals 1, with an open circle at each end. At x equals 0, there's a fill dot at 0. At x equals 1, a fill dot at 2. Between 1 and 2, the graph sits at y equals 3 with open ends. Summary: at integers n, f of n equals 2n. Between integers, the function is constant at 2n plus 1 on the open interval from n to n plus 1. In this lesson, we will graph the function f of x equals ceiling of x minus floor of x, step by step, and build strong intuition for why the graph looks like a dotted line at 0 and floating steps at 1. First, definitions. The ceiling function gives the smallest integer greater than or equal to x. The floor function gives the largest integer less than or equal to x. For example, the ceiling of 0.5 equals 1, and the floor of 0.5 equals 0. Step 1. Analyze specific points and intervals. We will study the interval from 0 to 2. We will plot the key values at x equals 0, between 0 and 1, at x equals 1, between 1 and 2, and at x equals 2. At x equals 0, 0 is an integer, so the ceiling equals 0 and the floor equals 0, and f of x equals 0. We show a filled dot at 0, 0. For 0 less than x less than 1, the ceiling equals 1 and the floor equals 0, so f of x equals 1. We draw a horizontal segment at y equals 1 from 0 to 1, with open circles at the ends because the value at the integers themselves is 0, not 1. At x equals 1, 1 is an integer, so the ceiling equals 1 and the floor equals 1, and f of 1 equals 0. We place a filled dot at 1, 0. For 1 less than x less than 2, the ceiling equals 2 and the floor equals 1, so f of x equals 1 again. We draw the next horizontal segment from 1 to 2 at height 1 with open circles at both ends. At x equals 2, 2 is an integer, so ceiling equals 2, floor equals 2, and f of 2 equals 0. We place a filled dot at 2, 0. Step 2. Generalizing the pattern. If x is an integer, the ceiling equals the floor, so the difference is 0. If x is not an integer, the ceiling is exactly 1 more than the floor, so the difference is 1. We can write the rule compactly as a piecewise function. Step 3. Draw the full graph. Between every pair of consecutive integers, we draw a horizontal segment at height 1 with open ends. At each integer, we place a filled dot on the x-axis at y equals 0. This pattern repeats forever. To read this graph, the filled dots at integers sit on the x-axis with value 0. The floating segments at height 1 indicate that for any non-integer input, the output is 1. Here is a simple legend to lock in the idea. Summary: when x is an integer, ceiling equals floor, and f of x equals 0. When x is not an integer, the ceiling is exactly 1 more than the floor, so f of x equals 1. Welcome! In this example, we will analyze and graph the function f of x equals floor of x minus ceiling of x. We'll build intuition step by step, and then draw the graph clearly. Step 1. Define the function's domain and range. The function maps real numbers to integers, and it is given by f of x equals floor of x minus ceiling of x. Step 2. Consider two cases, when x is an integer and when x is not an integer. For integer x, the floor and the ceiling both equal x, so f of x equals 0. For non-integer x, write x equals n plus a with n an integer and a between 0 and 1. Then floor of x equals n, while ceiling of x equals n plus 1, so f of x equals -1. Step 3. Use a key identity to connect floor and ceiling. The identity is ceiling of x equals negative floor of negative x. Substituting into f of x equals floor of x minus ceiling of x gives f of x equals floor of x plus floor of negative x. This alternate form still leads to the same piecewise behavior, 0 at integers and -1 otherwise. Step 4. Let's graph the function. We will draw axes and then plot two features, closed blue points at y equals 0 for integer x, and horizontal orange segments at y equals -1 between consecutive integers with open endpoints. First, plot the integer points with closed dots at height 0. Next, Plot the segments between integers at height -1, using open circles at the ends. To summarize the rule on the graph, for integer x, f of x equals 0. Those are the closed blue points on the x-axis. For non-integer x, f of x equals -1. These are the horizontal orange segments with open endpoints. Quick check, what is f of 2.5? Because 2.5 is not an integer, the value is -1. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.